All right, let's look at how we do this so-called dot product or inner product. I made a summary about the properties of dot product over here. So it's going to be really convenient because sometimes we may not remember the formulas. So over here we have formulas for the angle, cosine of the angle, and also we have the projection and this is vector projection and also the component projection, so-called scalar projection. All right, so we are going to go directly to the examples. All right, let's look at example 1. Given a vector 1, 2, 2, so this is in 3D, find the direction cosines of the three angles between the vector and the three coordinate axes. So let's first just sketch the diagram over here. So in general, if you have a vector over here, you can find three angles. This is x, this is y, and this is z. So this angle over here is called alpha, and this angle is called beta, and this angle is called gamma. Okay, and we have a vector over here, 1, 2, and 2. Okay, and you can see in general, it isn't very easy to find the angles. But on the other hand, since we know that the angle between two vectors are given by the dot product divided by their lengths over here, so we actually can easily find. But let's say we call this A over here is 1, 2, 2. Then cosine alpha is going to be this A vector dot product. The x-axis is 1, 0, 0, and divided by A, and also this vector 1, 0, 0. That would be the cosine alpha. But you can see the length of this vector is 1. It's called unit vector. So this is going to be exactly over here. We have A's length over here. And on top is simply going to be 1. Because we know the dot product of 1, 2, 2 and 1, 0, 0 is the sum of the corresponding product. So it's just going to be 1. Okay. So so continue. We're going to try to find out what's the length of A. The length of A, we know it's a square root of 1 squared plus 2 squared plus 2 squared. And we are in a very lucky case. This is 1 plus 4 plus 4. And that's going to be exactly root 9. And it's going to be 3. So this one over here is exactly 1 over 3. Okay. All right. Once I've finished this one, we can try it again. But for other two, we're going to do it a little faster. So cosine beta is going to be A over here, dot product 0, 1, 0. And over here is A vector's length and 0, 1, 0, like that. And then again, we know the length of A is 3. And this one over here is going to be 2/3. Okay. And cosine gamma is going to be, again, the same thing, 2/3. Okay. In fact, we know that cosine alpha squared plus cosine beta squared plus cosine gamma squared is always going to be 1. 3 cosines. And this is simply saying that the vector over here, cosine alpha, cosine beta, and cosine gamma, this one is so-called the unit vector for this 1, 2, 2 over here. Okay, and this is just the length. All right. So if you look at what we have, is that these are exactly 3 components divided by the length, right? So if you look at this one over here, the vector we have is exactly 1 over 3 2 over 3 and 2 over 3, right? It's simply 1, 2, 2 divided by the length 3, and that's always going to be true. All right, now let's pause, and then we're going to continue to do the other two problems, okay? All right, for number 2, find the scalar and vector projections of B and to A. Now, it matters if you project onto A to B or B to A. So if you have B over here, and if you have A over here, when you project onto A, that's a vector in A direction. So you do the projection. This is a so-called orthogonal projection. So you always draw a perpendicular line over here. And then this one over here is going to be the projection of B onto A. And the formula over here is because the projection onto A of this vector B. Okay, and that's going to be AB, the dot product, divided by the length of A divided by the length of B. And you still need to get onto the vector A. So if we look at this back over here, how to find it over here is the projection over here. Actually, I think it's over here. It's this one. Okay, so in fact, this one over here is A, and this one over here is going to be A. Okay, so the only thing we need to we need to actually calculate is that we need to do A dot B. This is the one, and also we need to find A squared. That's just the norm squared. So it's going to be -2 squared and plus 3 squared and plus 1. That's going to be 4 plus 9 plus 1, and that's going to be 14. Okay. If you look at the formula of this scalar projection and the vector projection, you can still see a scalar projection over here, the component projection, A, B over here, is part of the vector projection. But this part is going to be a number, right? So if you look at this one over here, it's part of it. So we can easily write down now both the vector projection and the scalar projection. What we need to do is still find the dot product. The dot product will be 1 times -2 plus 1 times 3 and plus 2 times 1. So let me squeeze it over here. So that's going to be -2 and plus 3 and plus 2, and that's going to be 3. So we have the projection of B in the direction of A. That's going to be 3 over 14. And here we have, because of vector projection, so we have -2 and 3 and 1. Okay, and you can multiply the constant through or not, but that's not going to be a problem. Okay, so how about the component? Component, that means in the A direction, how long the B is going to be. So this is going to be 3 divided by the square root of 14. And this is a number. This is a scalar. It's a number. Okay. Now, that's all we have about the projection. So this is a vector, and here is the scalar. All right. So when this scalar is positive, that means the projection of B is in the same direction of A. If this scalar is negative, then we will see that it's on the other side. For example, if you have something like this, and if you have B vector like that, if you have a B vector, say, like this is B vector. And then the projection over here is in the other direction of A, and you will see that the component of projection is going to be negative. Okay. All right. Now, but in our case over here, we have positive. Now, the last problem over here is just based on our observation. So if you look at what we have over here, this is A, right? And this is B. Okay. So if we project down over here, then we have a vector over here. This one over here is a projection of B in the direction of A. Okay. Now, if you look at this vector over here, this vector over here is exactly B minus projection of B onto A, right? Because if you look at it over here, that if we call this vector over here, let's say we call it V, okay? And this vector over here is B minus V, right? It's B minus V. So if we add these two vectors, V plus B minus V is going to be simply B over here. So this vector over here we see, because by the nature of the this projection, should it be perpendicular to A? How can we do that? We know that we can actually try to find the dot product of these two vectors, and B minus projection of B in the A direction. So if we do that, then we know that the dot product has distributive law. So this is going to be A dot B over here, okay? And minus A and dot over here. We have the formula over here. So this is going to be A dot B over A norm or length squared. And this one over here is a number, and we put A over here, right? That's the one. So if we do that, this is a number. So what we have over here, this is exactly a B vector, the dot vector. Now this one over here is a number, so we can factor it out because we have a scalar, and that's going to be A dot B, and over here A squared. And here we have another dot product. Okay, this is another dot product. But we know that A dot A is exactly its length squared, right? And then we cancel these two, and this is exactly 0. All right, these are three simple